Strathclyde. So yeah, when we're talking about vibration measurements in radar, we're talking about using the microdoppler effect. So microdoppler is frequency shifts observed by radar due to micromotions, be that vibrations, oscillations, rotations, anything that has a kind of periodic nature. And these can be useful for classification or activity measurements. So a classic example of this is differentiating between radar measurements of drones and birds. So they both have the same velocity and thus the same kind of bulk Doppler, but if you're looking at microdoppler, they're very different signatures. This is because drones will have very fast spinning propeller blades versus slow flapping boat. And I'm interested in doing this kind of measurement from synthetic aperture radar, so SAR. And Spaceborne SAR as a technology offers very high area coverage, day, night, and all-weather operation, and frequent revisits. So measurement measurement of microdoppler with SAR then benefits from all these advantages. And this project is part of the ESA EO for Security microdoppler project, which seeks to consolidate techniques in this area. So I'm not sure if everybody in this room knows exactly what SAR is, so I'll just go over it briefly, although Nicole has definitely covered some of this already. SAR satellites produce images from a series of transmitted and received pulses along the flight path, and synthetic aperture is the distance traveled along the flight path during the observation time, or dwell time. The aperture is then synthesized by applying phase corrections, accounting for the change in position for each pulse, and this improves the azimuth resolution. Over the course of this project, we're looking at a number of different use cases. So this includes non-cooperative target, maritime target recognition, where we're seeking to essentially map vibrational signatures of vessels at sea and use this as a classification feature. We're also looking at marine radar on-off detection, where we're looking for the signature of the spinning radar. And we're also investigating the use of microdoppler features and techniques for the detection of humans from SAR data. So for this talk, I'm talking about the specific use case of structural health monitoring. Vibrometry for SHM detects structural changes indicative of damage by comparing different spectra at different times of the same structure. So you measure the vibrational signature of a structure as natural modes. If those modes change over time, it indicates that something has changed in the structure. You generally need to investigate that. So SHM of bridges typically is achieved by in-situ sensors such as accelerometers. And installation of these can be expensive and time-consuming, so it might be difficult to get access to the parts of the bridge that you need to put the sensors on. You might need to close the bridge, which obviously has economic impacts. And additionally, once they're in place, they provide a point measurement, so their coverage can be limited, and you might need more than one. SAR, as I was explaining, is non-contact and has broad coverage, so it can provide a potential solution to all of these issues. And in fact, it can potentially monitor all the bridges in the city simultaneously. So this is an image of Glasgow from SAR, and just to highlight all the bridges that I can find, this can emphasize the potential power of these techniques. So SAR SHM has been shown before, but crucially not with synchronous ground truth, so this is a key novelty of this one. So just to cover some SAR microdoppler measurement principles. SAR localizes targets and azimuth, as we were saying, by synthesizing aperture over the observation time. However, for microdoppler measurements, we also need time localization. So to do that, we form what's known as subapertures. To do this, we return back to our SAR geometry diagram. We have our synthetic aperture length, LA, or LSA, and you can divide this by a number of subapertures to form different images. So you can take the data from time equals A to time equals B, and call that subaperture 1, and take time from B to C, and call that subaperture 2, and then form individual images from those to create your subapertures. So what does this look like? We go from this, which is an image zoomed in again of Glasgow, formed with the full aperture length, to this, where this is a subaperture image. Now you'll note, going from this to this, we lose some azimuth resolution. However, crucially, we now have more than one image separated in time, which allows us to essentially trade azimuth resolution, time resolution, which means we can then make our microdoppler measurements. So the formation of subaperture images in this work is achieved by using the back projection algorithm. Back projection algorithm in its general form is used to focus SAR images, and it works by forming an image grid of pixels, and essentially you go through each pulse and project onto that image grid the information and account for, you apply phase changes which account for the range to the pixel and platform velocity for each pulse. Then you sum all that up and you can create an image. However, in this work, rather than the final summation, we concatenate each of those pulse images to form a data cube, where again these are subaperture frames separated by time. We also batch some of these pulses and integrate them together just to increase our SNR. Now, I should emphasize this is a novel method. Subaperture formation hasn't been done like this before, and the benefits of this are that the phase is directly preserved, and thus all established microdoppler techniques are applicable to the signal. So in our broader microdoppler processing pipeline context, we've done this step as subaperture formation. So we can now move on to pre-processing. Essentially, we take a pixel from the scene, as shown here, and we take each pixel from all the subsequent frames and form our signal of interest from this. We then perform a mean subtraction and a low-pass filtering step just to clean up the signal a bit. Then we move on to our microdoppler measurement section, where we use standard time frequency analysis methods of the spectrogram and cadence velocity diagram, the cadence frequency spectrum, to essentially extract the vibrations of interest. The tunable processing parameters are the number of pulses per batch, the low-pass filter cutoff frequency, and the spectrogram window size and overlap. So our data were collected on the 16th of May 2024 of the South Portland Street Suspension Bridge in Glasgow, Scotland, as shown on the map here. The suspension bridge is a 126-meter steel footbridge across the River Clyde, which runs through the centre of Glasgow, and the data were acquired using the Umbra constellation and supplied in the CPHD format, which is compatible with the BPA algorithm. So this is an image formed from that data using the back projection algorithm. And on this, I've annotated the locations of the ground truth sensors, so all the accelerometers. These were linear accelerometers, and they were placed on the bridge in pairs, one in each pair being horizontal orientation, one being vertical orientation. This was to capture the different modes of movement of the bridge. And then from this data, a velocity time series was calculated by integration, and this was synchronized with the SAR data by the comparison of the timestamps. So now moving on to our results. The vibrational measurements that I'll be showing are for the accelerometer pair A4, so in this circle here, and the SAR measurements also come from the pixel within the purple circle. So this is what the two spectra look like. So we have A4, which is the accelerometers in purple, and SAR measurements in black. These spectra were normalized to the peak value in each case to aid comparison. And the tuned parameters were a cutoff frequency of 10 Hertz for cluster and noise removal, batch size of 25, and a window size of 50, an overlap of 98% for the spectrogram. So this table shows a comparison of the accelerometer and SAR modes which were detected in both. And just to highlight them, I've added these arrows. So important thing to note here, looking at these absolute errors, is that the measurement uncertainty of the SAR spectrum is the DFT bin width, which is 0.045 Hertz. And 5 out of 7 of our recovered modes fall within this value. So it shows that we've got a decent level of accuracy for these preliminary results. We also have detected some spurious frequencies, which are potential processing artifacts. So these could be harmonics from the CVD, the cadence velocity diagram. We also note that the relative amplitudes in general do not match between the spectra. So as you can see, the peaks are all different sizes in comparison to one another. However, this isn't particularly unexpected as the CBD magnitude depends on the target reflectivity, whereas the accelerometer magnitude depends on the displacement of the bridge. So in conclusion, this presentation has shown some promising results from preliminary work, where microdoppler extraction techniques have been used to yield some useful frequency estimates from SAR data. In terms of future work, we're looking at methods to integrate our data to provide improved SNR for our spectra, and we're looking at alternative microdoppler methods to analyze the signal formed using the modified back projection algorithm. Specifically looking to improve our frequency estimate accuracy, reduce any of the artifacts, and improve the match of relative amplitudes. So that concludes my talk. However, I'd just like to thank members of the SSPNS labs and personnel from the Civil Engineering Department at the University of Strathclyde.